Oh, there we go. Hey, ReactiveConf. It's great to be here. My name is Bryan Phelps, and I'm really excited to be here today to talk to you about a code editor I've been working on called Onivim. I'm going to share with you today how we re-architected for performance. Not only is it faster, but we're getting a cleaner application architecture out of it too. And I'm the founder of a company called Outrun Labs. Before that, I was working at Microsoft on a variety of cross-platform and web applications. You can find me on Twitter, GitHub, Discord as Bryfe. And here's an overview of what I'll be discussing today. First, I'll give you some background on Onivim, just enough so we can talk about the architecture. Second, I'll describe our V1 architecture and the sort of challenges we faced. And finally, I'll talk about our V2 architecture, and the changes we made, and the results we had. So what is Onivim? It's a code editor, but it's kind of a niche one. It aims to combine a few different worlds. The first world is modal editing, like Vim. It's kind of old school, but a modal editor is one that has different modes. And insert mode is one we're used to in like VS Code, Notepad, Word, where you type and insert letters. But modal editors have modes specifically for editing and navigating text too, with just the keyboard. The other world we want is a fast, beautiful interface. I think Sublime Text is the gold standard here. It shows that you can have a GUI that's really fast and performant, starts up instantly. Then we want top-tier language support. And VS Code is the standard here. It's just so good at understanding TypeScript and any language you throw at it. And the ultimate vision for us is to be the fastest way to go from thought to code, to take your idea and put it out into code through this editor. A tool that works for you, always keeps up, never makes you wait or pauses or takes you out of the flow. And it's been a journey, and we're not there yet. But for this talk, I'd like to take you on that journey with me and share some of my thoughts and learnings along the way. And hopefully, even if you're not interested in editors or Vim, the architecture pieces will at least be interesting. So let's rewind a bit and talk about the start of the project, our V1. So this is a screenshot of our V1, and it's really the same goals and visions. We shipped our V1 as a cross-platform Electron app, and we met some of these goals. But really, I think the most important outcome for our V1 was I found that there was a group of developers who were interested in this hybrid, interested in this kind of niche editor. We also experiment with some fun ideas, like Vim and modal editing is historically thought to be very hard to learn. You have to learn all these key sequences and commands. So we wanted to experiment with ways to make that easier. But it wasn't perfect. In particular, we struggled with performance. And it's cool to hate on Electron, like on Hacker News and stuff. But the reality is, there were issues that kept us from meeting that goal for our users. Part of the problem is that Vim users have a very high bar for performance. And so if we're not meeting that bar, then we're asking them to make a sacrifice. And we sort of pursued more and more investments to get the performance that we wanted. We also had some bugs around non-determinism with key presses, which are the worst kind of bugs you can have in an editor. And it was these combination of issues that led me to think about what an alternative architecture could look like. So let's take a look at the tech stack of our V1. So we have a standard Electron app, which has two processes. There's the main process, which is sort of the orchestrator of the app. And then there could be one or more renderer processes, which are the actual browser windows that you see. We also had a separate node process that was our extension host. And we used an open source project called NeoVim to handle all the Vim heavy lifting for us. And let's zoom into that renderer piece. So inside our renderer, we had a pretty familiar web stack. We used React and Redux. We used TypeScript, compiled to JavaScript. And for some performance critical pieces, like the actual rendering of the editor surface, we used WebGL. And I really like this stack for web applications and for desktop applications. And for whatever hate Electron gets, The reality is, it's never been easier for a small team to ship a cross-platform application. And especially to be able to ship cross-platform with confidence. What I mean by that is I can write my Electron app on one platform, and as long as I don't use a small set of platform-specific APIs, I can be pretty sure that it looks and feels the same everywhere. And that's pretty huge. But there were challenges for us. Otherwise, I wouldn't be giving this talk. As we built more and more, the application would get slower to start. And I kind of realized you don't really appreciate all that the browser or Electron or a JavaScript engine is doing for you until you profile. So let's check out a profile of the startup time. So it's a little confusing because the timeline starts at a half a second. But let's take a look at it. So overall, it took about 3.5 seconds for us to load the app. And this is just reloading the renderer process. And for the first second or so, you can see the screens, what's being rendered. We just have a blank screen. And you think about a second is literally billions of CPU cycles on the Intel i5 that I grabbed this profile. So it's kind of crazy. Finally, at around the 2-second mark, we get a title. So something finally shows up. Then we keep going. We start to get some UI. We see a tab come in and the cursor. We think we're almost done. But if you look at the top, there's still a bunch of stuff that we need to do before it's totally interactive. So the 2-second mark, and we keep going. And we have a sidebar kind of pop in. But then it's going to kind of pop out. And that's obviously a bug in our startup. We shouldn't have that jarring experience. It's transient, but you'll see it, and it just won't look right. And so finally, we hit our final rendering, but there's still this JavaScript work left. And now we're at a point where you can start using the application. So it's interesting to look where is all this time going? And if we take a look at the bottom row, these are all the steps that we're doing. So we're loading various JavaScript files. These evaluate scripts. Our Electron loading our JavaScript, parsing it, evaluating it, compiling to bytecode, and maybe jitting it. And it's an appreciable amount of time. So 300 milliseconds for this one. Garbage collection. This is another script that's loading, another 300 milliseconds. And so this time really starts to add up. And then there's an animation frame that fires here. That's a bug in our startup code. We should have fixed that because we really shouldn't be animating anything until we're have everything loaded. But coming from languages like C or C++ that are compiled, we're compiling code anyway with TypeScript. So it's kind of crazy. Why does it need to compile again when I run it? And I look around at other applications for inspiration. Vim starts up instantly. Sublime Text starts up instantly. Notepad start up instantly. Why can't my app start up that quickly? To me and my users, even a couple seconds is too long. So startup wasn't the only performance challenge. There were several others, but the main challenge on my mind was responsiveness. And responsiveness is the time from processing user input, like pressing a key, to showing a result on the screen. And ideally, we should shoot for the absolute minimum, ideally under at least 16 milliseconds, which is 1 frame at 60 frames per second. Games render at this rate, entire 3D scenes. Why shouldn't my code editor be able to do that too? And one challenge we had is we had sort of a back and forth, some asynchronicity in how we handled the key press. So a key press would come into our renderer process. We'd send that over to Onivim. And it's a separate process, so we'd send it over a pipe. That would get put on an event loop. And then it would send us a couple of messages back. It would send us some information about what changed with the buffer. It would send us what the screen should look like. It kind of represents it as like a grid of cells, like a terminal. But we also wanted to do some kind of rich rendering, like adorners, color widgets, minimap, tab indents. And to do that, we needed to know a little bit more about the window dimensions and the relation of the cursor position. So we had to make another call to get window metrics, sometimes more than one. And then we get some information back. And this would let us build up a map of a buffer position, a line and a column in a file, to a pixel position on the screen. And we need to do all this back and forth within a frame, within that 16 milliseconds. And then we'd actually have to render. And rendering wasn't always a trivial cost. And we actually did a lot of things to try and squeeze more and more performance out of our stack. First, we implemented bundle splitting. So instead of loading the entire JavaScript of the application at once, we split it up into bundles so it could be loaded piecewise and on demand. We also used async imports, so we could kind of parallelize the loading and load some things while we're evaluating other things. And we used minification to minimize the work that the JavaScript parser has to do. Less characters, it's less work. For runtime performance, to get that responsiveness, we implemented some things on top of that architecture. We implemented this feature called typing prediction. So what would happen is when the key press comes in, we would try and guess the result of that before it goes over to Onivim, and we would render immediately. The problem is, sometimes we would guess wrong. Like maybe it would be at the edge of the line, and we wouldn't know that the line wrapped, so you'd see a character kind of dart out to the side for a second. So it added some complexity and some bugs to our application. We implemented debounced rendering, so we had a Redux and React stack. And every time we sent an action into our Redux store, it would trigger the DOM to update. And it turns out this was very noisy for us. So we used this library that let us kind of synchronize it with request animation frame so that maybe a bunch of actions come in, but we only render it once during that animation frame. And we also ended up having to split our Redux stores. We had so much state there that the actual cloning of the objects started to show up in our performance profile. So by splitting it up, we minimized that cloning cost, but at the cost of extra architectural complexity. And finally, we spent a lot of time in the paint profiler, which is a really cool tool in Electron that lets you see how much work it's doing when it has to redraw the UI. And ideally, you want to keep that as small as possible. To be fair, we really stopped short of a few potential optimizations. Like one that could have helped our startup time is the ability to pre-compile JavaScript. But as a very small team, you start to reach the point of diminishing returns. And I could see us getting additional incremental gains, but not the instant performance of like Notepad++ or Sublime Text. And in the back of my mind, I was thinking, why do we even have to battle this? Why can't our desktop app, our technology, just be fast by default? And so I was thinking about our architecture from another perspective, kind of top down. And at the very foundation, we have sort of platform APIs, things like Cocoa, Win32 APIs, OpenGL, and then libraries that are common across platforms, things like harfbuzz and freetype for text rendering. Then we have Electron on top of that. And then we had Onivim to help us with the modal editing experience. Then we had a lot of NPM modules, and React and Redux at the top of that, and a bunch of transitive dependencies to support that. Finally, we had our application code sitting above that. But then it felt like we had all this sort of accidental complexity that we had to implement to get the performance we wanted. So these sort of things that aren't really core to the problem of building an editor, but things that we had to add to try and get that performance. What can we do about it, though? Well, for one, we're using WebGL anyway, and we're building a desktop app. We don't plan on shipping this in the browser. We could cut out the middleman and remove Electron. But if we get rid of Node and Chromium for our core editor, we have to figure out what we're going to do with React and NPM dependencies, because if Node and Chromium are gone, we can't really use JavaScript anymore. But maybe we could replace them with some streamlined set of native dependencies. I also wanted to switch our input handling to be synchronous. So when you press a key, we can render as quickly as possible. Remove asynchronicity from the path of pressing a key to rendering. And finally, I wanted to find a way to not have that accidental complexity, those extra features on the top of the stack. So I kind of came up with what my ideal stack could be. Like, what I really wanted was to have a React paradigm, but something that is all native code. Like, if we didn't have to evaluate the JavaScript, it could help our startup time tremendously. And if we had a synchronous model for handling input, we could process input and render immediately. So I really like the React paradigm of UI as a pure function of state, and also the Redux paradigm of your state as a function of previous state and an action. But I wasn't really sure how to get there. And I didn't really have an answer. I kind of considered just putting the project on hold because I didn't think we could meet our goals with the current tech stack. I thought about switching to C++ or Rust and using a UI framework there. There's lots of popular ones like Qt, but I'd miss that React style of UI development, that functional lean. But it just so happened around this time, I learned about an exciting project called Reason. And Reason's actually built by the creator of React, Jordan Walk. So imagine if you had a language that was purpose-built for React. It's a functional language, but it's pragmatic. You can do imperative, object-oriented programming. You can have mutable objects. It's geared and optimized for a functional approach, but also means you can be productive quickly without needing to climb an ivory tower of learning monads and category theory. It looks like JavaScript. It has JSX out of the box. But importantly for me, it could compile to native code. And it actually isn't really a new language. It's sort of a wrapper on an existing language, OCaml, which has been around for a long time. And it's invested in by various companies like Jane Street. So we started prototyping. And our very first prototype was really ugly. I mean, text rendering is horrible, no gamma correction. It really makes you appreciate all the things that Electron gives you out of the box. But we had the pieces we needed. We could render text, we could render shapes and icons. All the ingredients for a code editor. The rest is just details and cleaning it up. But we realized some of the pieces could be more general than a code editor. So we factored it out into a UI framework called Revery. And it's a UI and application framework built on Reason. It's very similar to React. So ideally, you could take what you know about React and transfer it. Compiles to native code. And it's desktop only for now, but we'd like to branch out to mobile. This is what a minimal Revery app looks like. And if you squint and don't look too hard, it almost looks like JavaScript. The UI.start is a lot like React DOM render, just in the native world. And this is a little more involved example. This is actually the component for the root of that prototype. So it looks vaguely like React, like the view kind of looks like React Native. The style looks vaguely familiar. So it's similar paradigms. And there's actually been some cool stuff built with it. So we have an example app with some applications like this calculator app. Kyle Davies built this cool chess app that shows like mouse, drag and drop. And Ken Wheeler built this really cool drum machine app. And of course, we started working, and trying to get our code editor working. It's still pre-alpha, but we're moving forward. And the architecture that we landed on was a fast native code front end built with Reason. And this uses Revery for the UI and the application lifecycle. And we also created a library for Vim called libvim, which is agnostic of the terminal, but has a synchronous API that lets us have that synchronous flow of key press to render. And because the front end is native code, it really helps our startup performance. We don't need to load and evaluate JavaScript anymore. But we didn't get out of JavaScript entirely because we really wanted to leverage the VS Code extension model. So we actually still have a node process running in the back end. It's actually the back part of VS Code. So the extension hosts the interface for language services and other features. So that's what we're working on right now, is wiring that up. So it's kind of an interesting architecture because we get the benefit of a fast native front end while still being able to leverage the breadth and power of VS Code extensions. So looking at some performance numbers, the last build of our V1 took about 5 seconds to start. That's actually more than the profile I showed because this is measuring end-to-end from pressing the button in the terminal to launch it to actually having it be interactive. And our V2 takes about a half second to launch with the same file. So it's an order of magnitude difference. And then the memory usage is pretty different too. There's significantly less memory usage on startup for this small file. And I think there's still a lot of low-hanging fruit left for us in the native code world. Our drawing layer right now is inefficient, but still faster than what we had before. There's an optimizing compiler for OCaml that Reason can use that we haven't even hooked up yet. There's blocking I/O on our startup path, but it's still faster. So I'll show a quick demo of our latest master build. Still kind of alpha, still rough around the edges. Here we go. So I'm going to open up a JSON file. And I got my favorite VS Code theme here. It's called a laser wave. I'm going to open up a key displayer so that you can see what I'm pressing. J and K move up and down in Vim. And there's a bug here with my extension. It should be .cc. I just changed .c. And then there's this easy section above. I kind of want to move that after the build section. So I can use Vim's command, say move 13 rows up, highlight this, delete it, and then press % to move to the end of the block and paste it. My favorite feature though is like lightweight management of splits. So I'm going to open up another JSON file as a horizontal split. So it's on the top now. And I want to sync up a dependency, this Reason SDL2. So I'm going to grab this. I just yanked it, which is like a copy, and move to my bottom window. And paste it. So now I have the version synced up, but I'm missing a comma. So I'm going to insert at the end, add the comma. I'm done with the split. I'll jump into a Reason file now. And this is like a preview. We're working on language integration right now. So I just started hooking up diagnostics. So you see that squiggle and an error message, and you see it in the mini-map too. And then we're working on hooking up completion as well. So hopefully that'll work. Cool. So there's still a lot of fit and finish and polish and features we need to implement, but we're moving forward, and you can build something non-trivial with this tech stack. There's been a lot of people across the board that have helped kind of build out this technology. We've built on a lot of great open source projects, people in the Reason community, people help build Revery and Onivim. And a big thanks to everyone who's helped support the project, our backers and pre-orders. Cool. So that's it. Thank you so much for coming to listen to my talk.